We have seen how a stationary wave can be formed when we have two waves, two identical waves in opposite directions meeting each other, and how it can be formed on a string, and how the distance between two notes is actually half a wavelength. So let me summarize this understanding. Stationary wave is formed when you have two identical waves in opposite directions. Okay, meeting each other. That's the stationary wave. And an important property that is that the distance between nodes, let's be clear about this, between adjacent nodes is half a wavelength. Okay. Now we can apply this idea to other types of wave, and we can even apply this idea to tell whether something is a wave. So let's see. For example, let's talk about sound. We all know about sound. You're hearing my sound right now. Let's talk about sound. If I have a sound, we know that sound can be reflected. So, for example, if I shout at a wall, maybe of a closed room or in a valley, in a hill, if I shout, then my voice will go out to the wall or to a hill, and it will get reflected. It will get reflected, and I'll hear, right? And I'll hear an echo, right? That's my echo. So sound can get reflected. Okay, we may have experienced this sometimes. Now the reflected wave, if you shout or if you produce a sound wave traveling towards a wall of some kind, the wave can get reflected, and when the reflected wave meets the incoming wave, so when those two waves meet, they can actually produce a stationary wave. They can actually produce a stationary wave. Now it is a bit harder to imagine, and actually you can't see it like on a string. Right? On a string you can see the movement, but sound wave you can't see it. So how do we know if it's actually happening? And the way to know that it's actually happening is to look for the notes. Now we might imagine setting up a more controlled experiment, maybe not a wall very far away. Just for example, we can imagine having let's say a metal plate here, a piece of solid here, and maybe a loudspeaker here. Okay, maybe a loudspeaker here. So that's just control that, like this. So if that's a loudspeaker and it starts giving out a sound wave, and it goes to this piece of solid, this hard piece of solid, sound wave can get reflected. Alright, and when they meet each other, how do we know if there's standing wave in between. The way is to maybe use a microphone. Okay, we put a microphone here. Well, if the sound wave is quite long, you can actually stand, or yeah, that's one way. You can either use a microphone and connect it to maybe some instrument, which I'll talk about later on, or you can just stand here. All right, if there's a lot of space here, you can just try walking between the loudspeaker and this. Maybe it's a wall, all right, or a big piece of metal. So you can just try walking to and fro, or move the loudspeaker to and fro, connected to some instrument. Maybe connected to some instrument that will show a sound wave there. Right, this kind of instrument, for example, we can use something called an oscilloscope. I'll talk more about this later on. So in any case, either using this or by walking around, we can actually tell how loud the sound is as I walk from here to here. So as you walk from here to here, you'll find that the sound gets louder and softer and louder and softer. And it's the same if you measure it with an instrument. As you move your loudspeaker along this line between the wall and the loudspeaker, you'll find that the instrument will tell you that the sound amplitude gets bigger and smaller and bigger and smaller. So this is what we will observe, and we can understand that this is because we are going through nodes and antinodes, right? Because at the nodes we will expect the amplitudes to be 0 and at the or very small, and at the antinode we'll expect the amplitude to be bigger. So that's why we get the loud soft pattern. So for example, we might imagine that when I'm at this position, it is loud. Okay, and maybe when I'm here, it is loud. Maybe when I'm there, it is also loud. But maybe in between, at this position, it may be soft, and that position, that is soft. Okay, so this is what we may hear as we walk from there to there. We'll hear loud, and then we'll hear soft, and then we'll hear loud, and then soft and loud. So this corresponds to the notes. All right, the soft positions corresponds to the notes. Loud position corresponds to antinodes, where there's most vibration. And we can also, if I take a ruler, if I mark out the position, say when it is soft and when it's soft again, I can actually use a ruler to find the wavelength. So between soft and soft would be half a wavelength. It would be half a wavelength. And if I measure this distance, I can just times 2 and get the wavelength. So that's one way to actually measure the wavelength of sound. Right? That's one way to measure it. And if you look at this in another way, all right, if we can also look at this in another way and say that this observation, the fact that we get a loud, soft, this pattern shows that we have a stationary wave, and therefore this in turn shows that sound is a wave. All right, you can use this as experimental evidence to tell you that sound is actually a wave, because after all, we can't see sound. We can hear it, but we can't see it like when you pluck a string, or when you look at the waves on the sea, where it's clearly going up and down and moving around, as we know what a wave does. But in sound, you can't see it. So how do we know that it's a wave? So this is one way to tell that it's a wave. The very fact that it will generate this standing wave pattern, where you have a loud, soft, and loud, soft pattern. So this tells us that sound is a wave. So the stationary wave, therefore, can be used as evidence that to tell us whether something that we can't see is a wave. And this, we can not just use it for sound. We can also use this idea for, say, microwave. Right? Microwave, you've heard about, you know about microwave oven. Yeah, microwave is also given out by our mobile phones. So again, microwave is not something that we can see. How do we know that it's a wave? We can actually carry out a similar experiment where you have maybe your mobile phone on one end and maybe a big piece of metal on the other end, and you can have something to detect the strength of the microwave as you move to and fro along this line.